Okay, a quick recap here. I removed both of these MOSFETs. They're, as far as I can tell, they were in parallel with each other, and because they fried, the one I could tell specifically had an issue. I removed that, took the second one off. I came back and I put power into the board, hoping that after removing the bad MOSFETs, that at least the left-hand portion of this driver would work. There's actually a button down here, right here, that is supposed to run the left side forward and backwards, and then the right as well. But even doing that, removing these two circuits, or these two components, still did not let the left-hand side output turn on. So there's something else that's wrong with this board, and I'm not an expert at troubleshooting circuit boards, so not sure what to do next. I did find with this board on, I kind of looked around for some more components that may have failed. If you take a look right here, there's this little bubble that is not on this one. At first I thought this might have been a manufacturing, like some glue or something for manufacturing. We'll zoom in. But it turns out that that circuit, I think you can see that, that circuit's fried. That stuff that came out is whatever used to be inside of the component. This turns out, I looked up the part number of it. This is a MOSFET driver, so it is driving, oops, it's driving these MOSFETs. And I also noticed with power hooked up to the board, just running my hands over it, I noticed this component was heating up with just battery power applied to the circuit board. So my hypothesis is that this circuit, because it is heating up, it's robbing all of the energy or power to this other side, because I assume that they're probably sharing similar power and ground sources. So I'm going to go ahead and remove this and then try again to see if my left side drive will turn on, the left output of this drive will turn on. There's some error or indication lights here. They're flashing as normal, so I'm assuming that the microcontroller is still good. So I'll take this chip off, hook it up to power, and then see if I get any output from the left-hand side. Okay, so to remove this circuit or this chip, we have to desolder all of these individual legs. The surface mount components they take a little bit of practice to work with, as well as not some high dollar specialty equipment, but sometimes it's nice to have the right tools. Again, I don't have the right tools, so there's a technique that I think I can work with, and I've actually started on it. You take a X-Acto knife and cut each leg. Try not to be so rough with the legs that you cut into the printed circuit board. And you can see that I've already cut the legs on this side. This side I need to score the legs, and then I can take the chip and I can wiggle it back and forth until the legs break off. I don't have an X-Acto knife. This is a regular utility blade. I'll try and be careful as I cut this so I don't cut myself or destroy the circuit board. Found a plastic tool. We'll work it back and forth. See if we can break a leg off. Looks like all the traces are still intact, which is good. And I don't think I damaged any or cut any traces that were underneath the chip. So now what I'll do is I'll hook it back up to power, or at least confirm that none of these are touching, and then I'll hook it up to power and see if the left output works. Okay, some bad things happened while I was off camera and testing to see if the left-hand side worked. I had a couple more MOSFETs self-destruct in a very spectacular way, but it was not caught on camera, which is a little bit unfortunate because it was quite a large fireworks show. Well, before this happened, I connected up my power and ground, as they should be battery plus, battery minus. When I connected it up, I saw that this LED next to the B here was on. According to the operator's manual, this indicates that the power is flowing out of this side. That's what that LED indicates. So I took my motor that I had, hooked the power up to battery, or to the B side, and then I took the ground side of the motor and connected it up to here. That did fine for, I guess, a couple tries. The last try I did, this happened, and it fried these last couple of MOSFETs, or this pair of MOSFETs. I don't know why, after removing this chip and starting to say isolate the logic side from the power side, that the left-hand side still doesn't work when I just try to run the test buttons. I know what this chip is. It's readily available, Mauser and DigiKey, and they've got a decent data sheet. What I can do is poke around on the pins and find out if any of the signals, which I suppose I can hope to see, are being sent to the chip. If they are getting to the chip, then perhaps this one also got damaged the first time around when these pair were short-circuited. So maybe I'll come back and try that and see. These chips are only $6. It wasn't bad getting them off. Reinstalling an SMD chip like this is not terrible. It takes a little work and practice, but it's not bad. I don't see any damage to the circuit board with this, so in the end I could remove these and put new ones on. So I'll do some research on the circuit and signals this should receive from the microcontroller when it gets a signal to turn the FETs on, and we'll see if I can determine if this chip is bad or if this whole board is just shot at this point in time. All right, I looked up the data sheet for this MOSFET driver and figured out which pins are power and ground that power the chip, as well as what the necessary power requirements are for this this component. Based on the data sheet, supply voltage minimum is 9.5 volts and max is 15 volts. This is a 20-pin chip. Pin 1 starts right here next to this witness mark that they place on the chips. And pin 15 and 16 are the supply pins for this chip. This is pin 20 right here. So 20, 19, 18, 17, 16. And that reads on the multimeter of 4.8 volts. And then '15 is right here. That one also reads 4.8 volts. Ground pins, VSS pin number 4. 1, 2, 3, and 4. So right now my ground lead for my multimeter is connected at the battery negative terminal. So we'll just check to make sure we don't have any weird voltage drop anywhere. Pin 4 is here and I'm reading exactly 0 volts on the multimeter, so I don't have a voltage drop anywhere. I would say the traces for the power and ground pins on this chip are okay. The problem is that I don't have supply voltage, correct supply voltage. It's not within the range of 9.5 to 15 volts anymore. And I did some checking, looked at the circuit board before I began this adventure here of checking the power supply. And if I move from here all the way over to here, this is a DC to DC converter, and that's how they get their supply voltage for the MOSFET driver. This DC to DC converter is used as a step-up converter after doing some more looking at the board. I don't know why exactly they use a step-up converter instead of trying to find a voltage regulator that will maintain sufficient and regulated voltage to those MOSFET drivers. I can only speculate that they decided on a step-up converter because the input here can be anywhere from 7 to 45 volts DC, or 10 to 45 volts DC. And what they decided to do, they put a good size 5 volt regulator on this board the 5-volt regulator supplies, I think it supplies several different areas of the board, including the input to this DC converter. And as long as the input voltage is higher than what this regulator requires, then they satisfy all the requirements of the regulator here, 5-volt regulator. 5-volt regulator maintains sufficient voltage and current to the step-up converter over here, which then supplies the desired voltage for the MOSFET drivers. We'll take a quick look at that converter. So pin 6, and again, there's a witness mark here that points to number 1. So that's 1, 2, 3, 4, 5, 6. Pin 6 is the supply voltage, and it's right at 5 volts. It matches what it's coming out of the regulator. The output of this is set by, there's a resistor here and a resistor here at pin 5. That voltage divider sets the output voltage of this step-up converter. And based on their equation they have in the data sheet, I should be seeing about 13.75 volts to come to the MOSFET drivers. And the output of that is on this side of this resistor. And when I check that, I see 4.8 volts, just like I was measuring on pin 15 and 16 for the MOSFET driver. I don't know if the step-up converter failed. Got some feedback voltage from the original short circuiting of the output, and then frying those two MOSFETs. Or perhaps one of these biasing resistors failed. The tricky part with one of these resistors is that I have to pull the resistors out of the circuit in order to accurately check them. There are techniques and devices to test passive components in the circuit, but they're specialty testers, and all I have is a multimeter. I think at this point I am going to cease working on this board. I would have to at least remove these resistors to find out resistors at this down here in the right corner at this step-up converter to determine if the resistors are bad or if this chip here needs to be replaced. Now, without even doing that, if I consider what this board costs, the fact that this board is readily available, I can buy it tomorrow if I want to and continue on with the actual project that I wanted to do, and just, be more intelligent about what I'm doing and not fry it, then I'm probably better off ahead scrapping this board and just buying a new one. Without destroying these chips like I did, I think I would even end up having to replace all 8 of these MOSFETs because of the failure here. I want to say that destroying these caused these ones to have an internal failure as well, because I think they were partially conducting, and that's why I had voltage at this point, even without having these buttons, these test buttons depressed. So I would say that these MOSFETs here were internally damaged as well. And then all of that led back to this one in particular, this MOSFET driver being damaged, finding out that I don't have the necessary voltage to turn these on, have them function correct, and then narrowing it down to this step-up converter being bad. This chip is 50 cents. This one's $6.50. These are each about $4 a piece. So I would need 8 of these, and that's not including the resistor, the gate resistor, and I think this is a diode next to it that very well may need to be replaced as well. So I'm looking at about $40 worth of components to repair this board. Now, doing this for myself, that's fine, but if I'm, say, repairing this for a customer, it's not worth it when this whole board is $180 off of a supplier on the internet. This becomes more advantageous if this was a, let's call it not a hobby grade motor driver, and you can't just buy one on the internet. I might come back to it and see if I can figure out what's wrong with this portion here, because I could still use half of this board, say for testing on my bench. You know, this is still a capable motor driver circuit. I just have to figure out how to get power to this chip. Maybe I hotwire something and it's just a standalone setup on the desktop or my bench, and I figure out how to get the 13 volts here, or the 9.5 to 15 volts that this requires. And then this is just something I use on the bench to test motors and such. So that's my conclusion for now. I think what I'm just going to do is buy a new board and not mess that one up.